All right, so today we're going to peel back the curtain on something most of us in tech use every single day, but probably don't think too much about: the MySQL database. We're going deep, like way down into the engine room, the InnoDB storage engine, to figure out what's really going on under the hood.
So picture this. You type that simple command, insert into, and poof, your data is saved. But where did it go? I mean, where does it physically live? It's not just magic, right? It feels like a black box. But today, we're going to pry that box open.
Okay, so our journey starts by looking at something we all get: files, and then shrinking our focus down to the real fundamental building block of the whole database. You might think, okay, I create a table, it makes a file. And you're not wrong. When you set up a table, MySQL does create files on your server's disk, and you'll probably see these .ibd files hanging around. But here's the twist. This is not a file you can just open up and read like a text document. Oh no, it's way more interesting than that.
And this is where a lot of people get tripped up. You know, you can double-click a spreadsheet, like an Excel file, and boom, there's all your data in nice little rows and columns. An IBD file? Not so much. Trying to open it would just give you gibberish. That's because it isn't a file of your data. It's a file that contains an incredibly organized system for storing that data. And the core of that system is something called a page.
And this right here, this is probably the most important thing to grasp. Everything in the InnoDB engine, and I mean everything, every single table, every index, all your precious data, it's all stored inside these little fixed-size 16-kilobyte blocks called pages. Think of your whole database as this gigantic library. Well, the pages are the actual, pages in all of the book.
But don't let that page name fool you into thinking it's simple. Even this tiny 16 KB block is a marvel of engineering. It's not just a raw chunk of data. It's got headers, packed with metadata, special system records, and then, your actual data rows. And get this, it even has its own little mini index inside, called a page directory, just to find stuff within that single page. It's like a tiny, perfectly organized world.
Okay, so if the database is a massive library made of millions or even billions of these tiny pages, how on earth does it find the one page you need in a fraction of a second? Well, that brings us to the next layer of genius organization: the index.
When you hear index in the database world, what you should really be picturing is a structure called a B+ tree. And the absolute best way to think about it is as a super smart, self-organizing table of contents for all your data. Its one and only job is to get the database from point A to point B, from your query to your data, as fast as humanly possible.
So here's how this table of contents is laid out. All those pages we talked about, they're linked together in a tree structure. It all starts at one single page, at the very top, the root page. Now this page doesn't hold your data. Instead, it holds pointers, like addresses, to other pages one level down, called node pages. So you follow those pointers down through the nodes, which in turn point to other nodes, until bam, you finally hit the bottom layer. These are the leaf pages, and that's where your actual row data live.
The sheer magic of the B+ tree is just how incredibly efficient it is. Think about it. You could have a table with millions, even billions of rows. But to find any single one of them, the database only has to read a tiny handful of pages. It just follows the map. Start at the root, hop through maybe 2 or 3 node pages, and it lands exactly on the leaf page that holds the data you asked for. It's crazy fast. And just to give you a sense of the scale we're talking about, it's just mind-boggling. A B+ tree that's only 4 levels deep, meaning it takes just 4 hops, 4 page reads to find anything, can theoretically manage a database that is up to, wait for it, 26 times terabytes. That is a colossal amount of data, all navigated in just 4 simple steps. Wild. So, up to now, we've seen this beautiful, elegant, hyper-efficient system. It's a work of art. But what happens when this intricate machine breaks? What happens when one of those essential pages gets corrupted?
This is the error message that gives database admins nightmares. You check your server logs and you see this. This is a direct quote from a real person's log, their worst-case scenario playing out in real time. Corrupted page. A fundamental piece of the database's own map is unreadable. And just like that, everything can grind to a screeching halt.
So what causes this kind of disaster? I mean, it could be anything really. A sudden power outage, a faulty hard drive, even a weird OS bug. The real question, the important one, is how does MySQL's InnoDB engine protect you from this? What are the built-in safety nets that keep your data from just vanishing into thin air? Okay, meet hero number one, the double write buffer. Think of it as InnoDB's ultimate safety net. Before it writes a changed page to its final home in the data file, a process that could be interrupted, it first writes a perfect copy to this special, separate area. It's literally like making a clean photocopy of a document before you start marking up the original. If the server crashes mid-write, no problem. InnoDB can just grab that pristine copy and restore it, preventing a half-written, corrupted page from ever existing.
And here's hero number two, the transaction log, which you'll also hear called the redo log. This is basically a diary or a journal that meticulously records every single change you make to the data. So if the server crashes, when it comes back up, InnoDB's first job is to read this journal. It then replays any transactions that were completed but hadn't been fully saved to the main data files. This ensures that no committed work is ever lost. It guarantees durability.
But, even with all these amazing protections, disaster can still strike. Corruption can happen. And when it does, there's a last-ditch emergency procedure. You can actually start MySQL in a special force recovery mode. This basically tells the server, hey, I know things are broken, but please start up anyway. It often works just enough to let you get in with a tool like MySQL dump and pull out as much of your precious data as you can. Then you can build a fresh, clean database and load your recovered data back in. It's a lifesaver.
Okay, so we've seen how it's built, we've seen how it protects itself from disaster. So what? Well, now we get to the fun part. We get to put all this knowledge to work. Because understanding these internals isn't just for trivia night, it's the key to making your database run so much better.
This is the payoff right here. Knowing about pages and B-trees and recovery logs isn't just academic. It gives us the power to actually pop the hood and tune the engine for some serious performance and reliability gains. And check this out. Here are a few of the big levers you can pull. You can actually change the page size itself, maybe to better match your specific hardware. You can pick different row formats, which is huge for efficiently storing massive blobs of data. And you can mess with features like the adaptive hash index, which, get this, builds an in-memory hash table to make your most frequent lookups even faster than the already fast B-tree search. Each has its trade-offs, but now you know why they exist.
And if you think these are just minor tweaks, look at the real-world impact. This benchmark shows what happened when someone simply changed the page size from the default 16 KB down to 4 KB to better align with their SSD's hardware. The result? A performance boost of up to 70%. That is a massive, massive improvement from just changing one line in a config file. And the benefits don't stop at performance. This deep knowledge is so powerful that it's even used in digital forensics. By understanding exactly how pages and B-trees are laid out on a physical disk, investigators can actually reconstruct what happened inside a database. They can trace a sequence of events and even spot if someone tried to tamper with the data behind the scenes, outside of the normal database tools.
So, when you really get down to it, a database is so much more than just a digital filing cabinet. It's a complex, almost living system of pages, trees, and logs, all dancing together in this incredible ballet of speed and safety. Understanding it helps you unlock its real power. And it kind of makes you wonder, right? What other black boxes do you rely on every single day? And what incredible secrets are they hiding inside?